But before we can have that good time this evening, we have to have a good time this afternoon. So please give a very warm ShmooCon welcome to Gabriel, Landau, and Mark Maker.
Good afternoon, and welcome to our talk titled Hide Your Valuables, Mitigating Physical Credential Dumping Attacks. I'm Gabe Landau. I'm a principal at Elastic. I love Windows internals. I work on endpoint security features, particularly Windows side. My best known research is probably kernel mode threats and practical defenses at Black Hat, process ghosting, and my AV sandboxing work. I used to wear red. These days I wear blue.
Hey everyone, I'm Mark Mager. I'm the Endpoint Protections Team Lead at Elastic. My background is primarily in defensive tool development on Windows, as well as reverse engineering and malware analysis. So just to jump right in, I'm going to discuss very briefly the differences between physical and virtual memory. So physical memory is pretty straightforward. It's literally the RAM chips that are in your computer, and you have as much physical memory as you have RAM. For this talk, one of the primary things to remember is that on Windows, access to the physical memory is controlled and maintained by the memory manager component within the kernel. As for virtual memory is basically the OS and the CPU cooperating to create the illusion that each process on the host has its own private contiguous address space. This is essentially what the concept of virtual memory. Memory is divided into pages, which are typically 4 kilobytes or 2 megabytes in size. And there's a hierarchy of structures called page tables that are used to map virtual to physical pages and describe other attributes such as page permissions, including read, write, and execute. Each process has its own page tables and its own private address space. And a virtual address space is typically sparse, with most addresses invalid. If you've ever popped any process into a debugger, that's probably something you've seen if you've ever looked through that process's memory map. Individual pages can be backed by RAM, files on the file system, or the page file. And the memory manager does provide seamless access to non-resident memory via paging. And the operating system provides APIs such as read process memory for accessing the address space of other processes. So here's a snapshot of what a process's virtual address space looks like as seen by the sysinternals tool VMMap, if you're familiar. Each color that's on the screenshot corresponds to a particular memory region type, including unused, private, file-backed, as well as shared memory. And so at any point in time, any used memory may or may not actually be resident in physical memory. And if that's the case, when the CPU accesses it, the CPU will issue a page fault, and then control will be handed off to the memory manager, which will then follow up and attempt to retrieve the data from its corresponding backing store, which is going to be a file or a page file typically. So now that that's out of the way, what are attackers typically after within memory? The short answer to that usually is credentials. And on Windows, the biggest credential dumping target for attackers is the local security authority subsystem process, better known as LSAS. And what you'll find within LSAS is that it houses several critical services and is primarily responsible for managing security policy. The tidbits that attackers are really after, though, is they're trying to dump Kerberos tickets, NTLM hashes, and clear text passwords, among other sensitive data contained within LSAS memory. So with that sensitive data, adversaries will use the credentials collected from LSAS primarily for privilege escalation, persistence, and lateral movement. So how are actual credential dumping attacks carried out? For the virtual memory side of things, a few of the common tools that you might have heard about that attackers typically use are procdump and mimikatz. The common thread with these two tools is that they both rely on the NT-read virtual memory syscall, where the OS will switch to the address space of LSAS and copy out the memory that's requested. Since this copy operation is against virtual memory, any page faults are going to be handled transparently by the kernel and should be invisible to the user. So for mitigations to Mimikatz and ProcDump and those tools of that nature, Microsoft introduced a way to run LSAS as a protected process light, or PPL. Processes that are secured via PPL are much harder to target with the anti-read virtual memory syscall. PPL also does provide mitigations for several other types of attacks you might be familiar with, such as the process forking or code injection, but those are out of scope for today's talk. Another type of attack that I'd like to discuss today very briefly is one that we've been seeing quite a bit pick up in prominence over the last year or so, and that's bring your own vulnerable driver, or BYOVD. The primary advantage that these attacks provide is that they provide a reliable way to circumvent the protections that are afforded by PPL. So typically what a BYOVD attack looks like is that adversaries are going to load a signed driver with a known vulnerability, and then they will later exploit that driver in order to get it to perform actions with kernel level privileges. Essentially this is done to disable or otherwise bypass PPL. In response to this attack vector, Microsoft at least blocks known vulnerable drivers by default in Windows 11, and it's optional in Windows 10. So I've covered virtual memory attacks. Now, to get into physical memory attacks, that's another avenue that attackers can explore for acquiring memory in order for extracting credentials. There's several methods to accomplish this. So when Windows blue screens or bug checks, it will save a memory dump to disk for error reporting and debugging purposes. This memory dump mechanism can be configured to save all physical memory to disk. Another option that you can pursue is the physical memory device, which is a section object created by the kernel that enables access to physical memory. Direct access to this device is facilitated by forensic tools via signed drivers, including WinPMM and Dumpin. And one primary advantage to this approach is that Microsoft's block list does not typically include such drivers like WinPMM due to their benign use. And virtual memories are also susceptible to additional threats. When a VM is suspended or snapshotted, a copy of its physical memory is going to be saved to a file on the host disk. And then this raw memory dump can actually be converted to standard DMP format using tools such as VMSS2 Core. So now that you have a physical memory dump file, what exactly can you do with it? Well, Mimikatz includes a tool called MimiLib that runs as a WinDebug extension, and that's used to load symbols and access the user mode memory resident within LSAS in order to dump credentials. Another option is a tool called VizMem2Profit, which basically employs a client server model and is network-based. So the server runs on the target and loads the WinPMM driver and exposes it via network socket. The client on the attacker's machine will connect to this socket, and it will pull physical pages on demand by the user over the network. And the recall forensic framework is used to assist with walking the page tables and any kernel-related structures, reconstructing LSAS's address space from physical memory. VizMem2Profit creates user mode mini dumps, which can then be processed with more standard tools like Mimikatz or PyPyCats. And then one other option is recall and volatility do include Mimikatz plugins that function very similarly to the MimiLib WinDebug extension on acquired physical memory dumps.
So that all sounds pretty bad. What do we do about it? Well, let's talk about mitigations. So going back to our VM map example, processes data that's physically resident is called the working set. Pages in the working set can be categorized as either private to this process or shareable with other processes. Today we're going to focus on the private working set because it includes the process's heap, which often contains these sensitive secrets that we're talking about for LSAS. If you look at the image there, you'll see the private WS column is highlighted in red, and we can see about 3 megabytes of resident memory. Windows provides the empty working set API to empty a process's working set. Now watch what happens when we run it. We can see the 3 megabytes drops to about 100 kilobytes. When you empty a process's working set, its pages aren't removed from memory immediately. Instead, the memory manager keeps a few caches of recently used pages in case they're needed again in the near future. One such cache is the standby list, which is a list of unmodified pages that can be discarded at any time if the OS needs some free pages. Another is the modified list, which is a list of modified pages that can't be reused until they've been flushed to their backing store, such as the file or the page file. We can use an API to have the memory manager flush both of these caches, removing them from physical memory. We created a tool called Silhouette. It's a kernel driver that detects changes to LSAS's working set, flushing it in response. Because it's a kernel driver, it's compatible with run as PPL. It doesn't have to deal with any of those PPL protections. It includes a file system mini filter to detect paging I/O, so it can quickly reflush the pages after they've been brought resident. So I'm going to give a quick demo of Silhouette against FizMem to Profit. So what we have here is we're running FizMem to Profit, the server, and it's running on the victim's machine. I'm sorry, I should speak into the microphone. On the top is the FizMem to Profit server. It's running on the victim's machine. And on the bottom, we have the client, which is actually running on an Ubuntu VM. And just to keep it all on the same screen, I'm running the commands over SSH. So we're SSHing to the attacker's machine to run the commands. So it's loading up the WinPMem driver, and it's generating a dump of LSAS right here. And it just generated. Now it's still on the attacker's machine, so we're going to SCP it to the local machine, and then we're going to run Mimikatz against it. And then when we look at the output, we can see that Mimikatz successfully collected hashes. Next, we're going to run dump it, which is going to generate a physical memory dump of this machine. It takes a couple seconds. And then we're going to pass that physical memory dump to Windebug, and that's going to load Mimilib, the Mimikatz extension, and extract credentials from that. So we're going to scroll up the output, and you can see we've extracted some secrets. So we're going to clean up now, and then I want you to look in the top right corner, and you can see there's about 9.3 megabytes of private working set for the LSAS process. So what we're going to do is we're going to start the Silhouette driver, and that private working set goes to 4 kilobytes, and perhaps more importantly, stays at 4 kilobytes. So now we're going to redo the 2 attacks we just did. First is FizMem to Profit. And it encountered an error. But let's try to collect its dump. So maybe it corrected a partial. No, there's no dump, so there's nothing. We can't run Mimikatz against anything. So now we're going to run dump it. And then we're going to take the output of dump it, and we're again going to pass it to Windebug and into Mimilib. And if we look, Mimilib had an error and failed to extract anything useful. Thank you. Okay, so it's great that we're able to break these attacks, but there's tools out there, such as the Recall Forensic Framework, that given a timely copy of the page file, can work around non-resident pages by paging in the missing data during analysis. So let's take things a step further and consider attackers capable of this. While Windows is running, it keeps the page file locked to prevent access. Attackers can work around this with tools such as Invoke Ninja Copy that access the raw disk directly, bypassing the file system. Invoke Ninja Copy, for example, will parse the NTFS data structures on disk, the master file table, and locate the file's data and then copy it. Silhouette can detect and block such direct disk access, protecting both the page file and the hibernation file. Unrelated to Silhouette, Windows has a built-in feature called NTFS page file encryption that you can use to also mitigate this attack. It ensures that the page file contents are always encrypted before they touch disk. Another bypass involves creating a volume shadow copy snapshot, and because the OS does not lock pagefile.sys within these shadow copies, that protection I talked about before does not apply to the page file version in these shadow copies. Silhouette can also detect and block these types of access is because the NTFS file ID in these shadow copies for pagefile.sys is exactly the same as the file ID for the original pagefile.sys. All right, so let me give a demo of this one, and hopefully I can see the screen well enough. Okay, so we're going to start, we're performing a traditional copy of the page file, and we can see that the regular copy fails. Now we're invoking invoke Ninja copy, which accesses the raw disk, parsing the MFT, and copies the page file successfully. Now we're going to use hobo copy, which creates a volume shadow copy and acquires the page file off that shadow copy. And that one's successful. Now we're going to start the silhouette driver, and you can see its output in the bottom in debug view. And we're going to redo the two attacks. So first one is invoke Ninja copy, and we can see that fails. And if you look at the bottom in debug view, you can see that silhouette detected it and blocked it. And then hobo copy also had a failure, and you can see that silhouette right there detected and blocked it. So let's talk about defeating this mitigation. Full memory dumps are slow, but fast attacks should be spammable. Silhouette ensures that pages are only briefly resident, and this window is much shorter than the time it takes to perform a full memory dump. An attacker repeatedly issuing RPC requests to LSAS while using a driver like WinPMem to perform surgical reads targeted just at LSAS's address space may eventually win. To mitigate such attacks, defenders should block drivers that allow physical memory access, such as WinPMem and Dumpin. A variant of this is the Windows Error Reporting Secure Process Dumper, or WRFault Secure. An attacker with admin rights can run WRFault Secure as a protected process and use it to dump LSAS. WRFault dumps are encrypted these days, so you can actually extract useful information from them, but the act of touching those pages will bring them resident. And so you could then pair that with like a WinPMem in order to try to pull the pages that way. To defend against this type of attack, a driver could use an object manager callback or OB register callbacks to block the process VM read permission even to protected processes away from LSAS. That would prevent such types of dumps. Another attack is to disable, move, or dramatically shrink the page file, so the pages have nowhere to go. So it requires a registry modification and then a reboot. Potential mitigations include monitoring for such changes with your EDR, locking the registry value from the kernel, or if the change is detected when the system starts up, revert to a known good configuration and restart the machine. As for future work, well, these principles can be applied offensively too, many from user mode. You can remove your implant from physical memory with 2 API calls. Think about that for a second. It's easy to extend the silhouette's volume shadow copy to other files too, such as the SAM registry hive or ntds.dit. So you can break hobo copy and invoke Ninja copy, not just for the page file, but for many other use cases. So as for my wish list, as is, Silhouette must flush the standby and modified lists system-wide. Ideally, we could do it only for the pages belonging to a specific process, but that's not an option today. While the EFI lock on run as PPL is great, its scope is really limited, and I wish we could lock more configuration options with EFI. So in summary, as you just saw, keeping LSAS's private memory out of physical memory stopped both physmem to profit with Mimikatz and dump it with Mimilib. Silhouette blocked Ninja Copy's attempt to collect the page file via raw disk access and Hobo Copy's attempt via volume shadow copy. We did some basic benchmarking, emphasis on basic, and there wasn't any noticeable performance hit, but overhead will vary based on your workload and your hardware. We'll be releasing Silhouette source code later today on GitHub. In conclusion, understand that physical memory is not omniscience. Paging is often taken for granted and happens more often than you think, especially on systems under heavy memory pressure. As for recommendations, we suggest running LSAS as a protected process, aka run as PPL, and enabling that UEFI lock mechanism. Enable Credential Guard if your environment and hardware support it. Deploy Windows Defender application control vulnerable driver block lists, and include forensic memory dump drivers in your driver block list. Any questions? Yes? It's going to be, I put the URL It's on the bottom line right here. I put it on the company Elastic's GitHub. Yes?
So, I saw that one of the mitigations is credential guard, and we talk about that, but I guess the question is, even though credential guard is enabled, have you found instances where once administrative access or administrative rights have been gotten, and that it pretty much eliminates the protection of credential guard?
So in Credential Guard, as we're talking about here, that actually runs it would store your credentials in a different virtual machine. So Credential Guard puts the entire Windows into a virtual machine, and then there is a separate secure kernel that runs, I believe it's a VTL1, that runs in parallel to you. And the physical memory device does not have access to that other virtual machine. It's as though you're running two VMs in VMware. One can't access the memory of another one. And the same issue, not just for the physical memory device, but even if you were to try to use raw page table access with like something like a PTE remapping. So you cannot get to the memory of that unless you go higher with something maybe like an SMM attack or that kind of thing. So that's it, we're out of time. So thank you.